So we want to start with the poll question. Have you ever encountered situations in which important information was stored as free-form text? Give you a few seconds to answer that. All right, so we're going to be talking about text vectors, which is a brand new HPCC machine learning library bundle that allows you to turn free-form text into rich numeric data that can be analyzed much more easily. It supports words, phrases, and sentences. Text vectors is fully automatic and unsupervised. You provide it some text, and it will convert it to numeric form. Now, interestingly, when it converts to numeric form, it's actually encoding the meaning of the text, not just doing a typographical transformation. We'll talk about this more going forward. Once the text has been encoded, TextVectors provides a means to do some interesting analysis of the data. We'll demonstrate some of this as we move forward. The encoded text vectors can be also be used as input features for any numerical machine learning algorithm. For those familiar with the vectorization algorithms, text vectors is a parallelized, enhanced version of the sent-to-vec algorithm. So let's take a look at the theory behind it. It may be surprising that an unsupervised algorithm with only the raw text as input can infer meaning, and also that it can transform the meaning into numeric form. I know it surprised me when I first learned of it. Let's try to understand this better by looking at the theory behind it. In 1957, hold on just a sec. There we go. In 1957, the linguist John Rupert Firth stated, "You shall know a word by the company it keeps." We can restate this more rigorously as the meaning of a word is closely associated with the distribution of the words that surround it in coherent text. Now wait a minute. I thought linguistic meaning was a deep philosophical concept, not a matter of statistical frequency. Let's do a thought experiment and see if we can get to the bottom of this. First, let's pick a few words that are fairly closely related. In this case, cat and dog. Now let's pick another word that's not normally associated with cat or dog. How about piston? We could find a lot of sentences that could equally apply to a dog or cat. A dog is an animal, a cat is an animal. Dogs can make good pets, and cats can make good pets. I have a companion dog, I have a companion cat. My son was bitten by a dog, my son was bitten by a cat. But there are a lot of sentences about dogs that would not likely be found about cats. For instance, my dog weighs 120 pounds. You wouldn't say that about a cat unless maybe you had a pet mountain lion. When I throw a ball, my dog brings it back to me. My dog barks whenever the mailman comes. Cocker Spaniels are a medium-sized dog breed. Now, keep in mind, none of these sets of sentences are likely to be found about pistons. Even my uncle, a true automotive enthusiast, didn't have a companion piston. Now imagine two words that would be interchangeable. There's no sentence about one that would not be likely said about the other. If we think about this long enough, we would have to concede that these two words must be synonyms. They have the exact same meaning. So cat and dog are similar, but not synonymous because they're interchangeable in some sentences, but not others. Yet piston is far from dog and cat because there are very few sentences in which they are interchangeable. Words that are always interchangeable are exact synonyms. So I guess Rupert Frith was onto something. A word is known by the company it keeps. To avoid philosophical argument, we call this notion of meaning contextual meaning. Now, contextual meaning is not absolute. It's relative to the collection of text upon which it is based. This body of text is known as the corpus. Any corpus we choose is likely to be a small subset of everything ever written, which is, of course, a small subset of everything that has been said, which is itself a small subset of everything that could be said. It may be that the contextual meaning and meaning converge as the corpus size grows toward infinity. So enough of the philosophy. Let's talk about the method behind text vectors. And vectors are simply a list of numbers, like 25, 3, -4, 5. It is useful to think of each vector as a coordinate in space. A two-dimensional vector can represent a coordinate in two-dimensional space. A three-dimensional vector can represent a coordinate in three-dimensional space. And an n-dimensional vector can represent a coordinate in n-dimensional space. For text vectorization, we usually use vectors of between 20 and 1,000 dimensions. These represent coordinates in high-dimensional space. Now we want to create vectors such that the words that are close together in space have related meanings, and words that are unrelated are far apart in space. This is an optimization problem. We start out with random vectors, and as we optimize, the vectors are moved until they arrive at the appropriate location where we've met our criteria. There are many ways to do such an optimization. Some of the most successful methods use neural networks. TextVectors uses a particular neural network-based algorithm known as the continuous bag of words, or CBOW. CBOW uses a specialized three-layer neural network shown here. The inputs are on the left, the outputs are on the right, and there's a hidden layer in the middle. Now the input and output layers each have as many neurons as there are words in the vocabulary, 1 through n, while the hidden layer has as many neurons as the dimensionality of the desired vectors, v. You can see that this creates quite a large network. A 100,000 word vocabulary with 100 dimensional vectors requires a network with 20 million weights that need to be adjusted during training. Special optimizations are necessary in order to train such a network in a reasonable time frame. So each word in the vocabulary is assigned a number from 1 to n. When we encounter a sentence such as dogs are fun, we move through each word in the sentence and set that word's context, which is the other words in the sentence, as the input to the neural network. We then train the network to output the main word, in this case dogs, and the context words are and fun go to the input. We then move on to the next word, are, with the context of dogs and fun. We do this until we've processed each word for every sentence in the corpus. By doing this, we effectively train the network to predict the probability of each target word given the context words. This is one embodiment of Frith's statement, a word is known by the company it keeps. Our goal, however, recall, was not to predict the probabilities, but to generate useful vectors. It turns out, though, that the weights that we train between the inputs and the hidden layer form excellent vectors, That's because in order to predict similar probabilities for similar words, those weights must also be similar. So we simply extract those weights and we have our vector for each word. To create a vector for a phrase or sentence, we simply average the vectors for each word. This approach works great for sentence-length blocks of text, but other mechanisms are more appropriate for handling larger units of text, such as paragraphs and documents. Another technique that's important for text vectors is the use of n-grams. N-grams are groups of words that convey a meaning that may not be inferable from the individual words. Examples are New York Times, high-performance computing cluster, or traffic light. The order of words in an n-gram is important. Traffic light and light traffic have very different meanings. This is what gives text vectors insight into subtleties of words ordering within a sentence. N-grams can be a sequence of any length. Using n-grams of length 3, which are known as trigrams, implies that we'll use bigrams and unigrams as well. Now let's look at a case study we did using text vectors. We used anonymized public records of legal offenses from several U.S. states. Each violation is identified by a violation description that is entered by hand by one of thousands of clerks at various courts. These descriptions have some interesting characteristics that make them particularly hard to process. They're very terse, sometimes only a few words. They're free-form, however that clerk decides to describe the violation on a given day. They use extensive abbreviations, and there are frequent typos and misspellings. We found nearly 1 million different violation descriptions and noted that around 300,000 new descriptions are entered in a given year. These descriptions used about 16,000 individual words, which swells to a vocabulary of 100,000 when we include bigrams and trigrams. Let's look at some of the results. So the training took about 40 minutes on a 20-node HPCC cluster to train the 1 million different descriptions. We identified, so the first result was we identified a set of interesting words in the corpus and asked text vectors for the closest words and meaning. You can see that when we asked about dog, it came back with dogs, cat, canine with 2 different spellings, and animal. We're definitely seeing that they are related by meaning and not just typographically. For boat, it found motorboat, an abbreviation for motorboat, MB, as well as canoe, aircraft, and vessel. Now, aircraft there is clearly a type of vessel, but it's also probably very similar in the laws to the boat, to a boat. So that's why you see some similarity there. For speeding, it found many different spellings and abbreviations, which it was able to detect as having similar meanings. Next, we limited the answers to a small set of potential words in order to see the spectrum of what words were considered distant as well as similar. Note that for dog, it found all animal words. For boat, it found various types of vehicle as well as the word crash. This shows the subtlety of the shades of meaning it was able to distinguish. Next, we played the game, one of these things is not like the other. We gave text vectors a series of words, dog, cat, canine, vehicle, terrier, animal, and reckless, and asked for the 2 most anomalous words. It correctly identified vehicle and reckless. All of the other words related to animals. Next, we gave it some descriptions that were not in the training set and asked it to find the most similar sentence among the violation descriptions used for training. It's interesting to see the mappings it was able to achieve. Given the first sentence, bicycles to ride to the right, it found fail to ride bike to the right and fail to ride to the right side, neither of which contained the word bicycle, yet were strong mappings in terms of meaning. If we skip down to the 8th row, we see that fictitious ID to purchase alco got mapped to fake ID to purchase alcohol. Another interesting mapping. Most of the mappings seemed reasonable and seemed to express the same concept in different words. The last sentence was included to show a case where mappings were not good. This was the case of an unprecedented sentence. There were no other similar violation descriptions. Note the item similarity on the right. However, the 0.79 similarity rating was quite a bit lower than any of the good translations. This indicates that although it picked the best mappings, that none were really similar. One of the interesting capabilities of text vectorization is the ability to handle word analogies. We had a hard time finding appropriate analogies to query, given the limited range of nuance in these first descriptions. We did, however, find one that made some sense. Fishing is to trout as hunting is to blank. Waterfowl and birds are reasonable solutions. We expected, however, to at least find deer among the top solutions. Moving on from the case study, the mechanism that TextVectors uses to solve analogies is very interesting. If we have a robust corpus, we can solve analogies such as Paris is to France as London is to blank. We do this by looking at the direction between the vector for Paris and the vector for France, and moving in the same direction and distance from the vector for London. If all works well, that should land us near the vectors for UK and England. Note that the direction and distance represented by the blue arrows is the relationship is capital of. We should be able to apply that same vector to any capital city and find the country of which it is the capital. Arithmetically, we just subtract the vector for France from the vector for Paris and then add the result to the vector for London. It's kind of a surprising approach. I think we're just beginning to scratch the surface in the technologies and applications for text vectorization. It provides a lot of useful benefits, but also opens the way for new frontiers. So that's the end of my presentation. We have a final poll question. Do you think text vectors might be useful for your projects? And with that, I turn it over to Bob.
All right, thank you, Roger. That was a very interesting presentation. I was riveted, and apparently everyone at the Tech Talk, too, looks like this was a really hot topic for them. First of all, the poll question, the first poll question that you submitted, have you encountered situations in which important information was stored in free-form text? A whopping 92% said yes. Only 8% said no. So amazing. And I think it just changed, went up to 93%. So yeah, people, this is a hot topic. People work with free-form text a lot. So let's take a look at the questions from the audience while the second poll is getting answered. And Roger, you've had a chance to prioritize some of the questions. So let's go with this first one here. Are text vectors still commonly used, or is this a technology that is being deprecated? Good question.
Yeah, so this is a fairly new technology. The sent-to-vec algorithm was developed in the last few years, and it is a state-of-the-art in terms of results. We compared it to most of the other techniques that could handle sentences, and it was seemed to be the best performing algorithm out there at this point. I think there are huge advances going on in this field, and we plan to incorporate new algorithms into text vectors as they come available.
All right. Let's see, what other question there? Let's take a look at some of these other ones here. I'm just going to go from the top. How do you do the distributed training of the neural network? I guess that's a pretty broad question there. How do you do the distributed training of the neural network?
Yes, so it uses a synchronous batch gradient descent, it's called. Essentially, we train on each node. A neural network is trained for a number of samples independently, and then at the end of that, what we call a batch, the weights are added together from all of the updates, and then it goes into a new cycle. So it uses the HPCC distributed processing capabilities to do it fully in parallel.
All right, thank you. I'm going to skip down to the one here at the bottom. Looks interesting. You said that you use the CBOW method to train the network. Do you also support the skipgram method used by word-to-vector?
Good question. So we do not currently use the skipgram method. There are two different methods for approximating first statement about the nature of words. One is the CBOW method, and the other is skipgram. They're very similar. The difference is that in one you train the probability of the target word gained given the context words, and in the other you train the probability of the context words given the main word. Some research has shown that combinations of these two methods actually work very well, and it turns out that we have an intern, I believe from Clemson, Farah Alshank, this summer, who is doing research to test these two methods and their interplay, and we plan to incorporate the results from that into future versions of TextVectors.
All right, sounds great. And just one more question, Roger. Thanks again for your wonderful presentation. What version of HPCC Systems platform do I need to run TextVectors?
It does require version 7 or above, 7.0 or above, so that's the only requirement.
Which I just upgraded to 7.24 today, so I think I'm ready to go.
You bet.
All right. All right, well, thank you so much, Roger. Let's just take a look at that last poll question before we move on, which was the, well, let's see, let's take a look at that one, which was, do you think that TextVectors might be useful for your project? 100% said yes. All right, that's impressive. That's pretty good. So good stuff here. Roger, looking forward to hearing from you again in the near future. And work with TextVectors.